Hello everyone. Let's talk about our recap from our last class. I think we were a little bit distracted after the test and I want to just recover this real quick. So we talked about our variation functions. You will find them chapter 7, section 11, page 383, and chapter 8, section 5, page 432. That's what we're going to talk about here in our little recap. So in our variation functions, we found that a variation function is an equation in which y is equal to a constant multiplied or divided by the power of x. And we can see over here to the right, if k and n are constants, then y varies directly with the nth power of x. And that means this general equation right here. Y equals some constant k times x to the n. And we also see that if it is divided by, it becomes inverse. So we see directly up here for multiplied and inversely when it's divided with the nth power of x, and that means y is equal to a constant k divided by x to the n. We talked about that in class, and we looked at two functions. We looked at the function of f of x equals 5x squared, and we looked at the function of g of x equals 162 divided by x squared. And if you recall, we were able to see where there was a pattern here. So we evaluated these at x and then the f of x, which we know equals y, and we evaluated this one at x and then g of x, which is the equal to y in this case. And we did the 1 and 3, 9 and 27. We found that when we plugged in the value of 1, we got 5. When we plugged in the value of 3, we got 45. And when we plugged in the value of 9, it was 405. And lastly, when we plugged in 27, we got 3,645. If you want to pause and check that out for yourself, you're welcome to. Just make sure to plug in those numbers for the x squared, so you'd be squaring them. We found that this was when we multiplied by 3, and each time we multiplied x by 3. And we found that when we multiplied x by 3 with this direct variation, this one, each time we went here, we multiplied by 9, which we also said was 3 squared. And for the inverse variation, we found we used 1 and 3 and 9. And we found when we plugged in those values, we got 162. We got 18 and 2. And we found here, we multiplied by 3. We, on this side, divided by 9. And this was also 3 squared. And through this, we were able to see a pattern that when x was multiplied by 3, we found that y was multiplied by 3 squared. And here we found when it was multiplied by 3, it was divided by 3 squared. So we found that we deduced our multiply pattern. The multiply property of variation functions. Now, over here on the other side of my screen, we're showing you, towards the right, we're showing you what those functions, those generic parent functions are, which we're familiar with at this point. So then, anytime we have these multiply property of variation functions, they do apply to our general equation variation functions. Our linear, when they vary directly, when it varies directly with the square, so cubic and quadratic, and then when we have our inverse ones too. So all of these properties of variation functions will apply to all of these general equations. So down here we can see the multiply property of variation functions written out as it is in your book, and it states that if y equals some constant k and our variable x the n, then multiplying the value of x by a constant multiplies the value of y by that constant to the same power as the equation. So in the example I just showed you, it was squared. So if we multiplied, and I'm going to scroll up so you can see, when we multiplied x by 3, our constant was 3. So then our multiply property says we will multiply by 3 squared. That same constant to the power in the equation, which is right up here. And the inverse is true as well. So then we used our multiply properties and our ideas to do a little example in class. Our example was the pressure required to force water through a garden hose depends on the number of gallons per minute you want to flow. By experiment, you find that the flow of 3 gallons per minute, you find you require a pressure of 10 pounds per square inch. For 6 gallons per minute, you need 40 psi. They want us to find what the pressure is required for a flow of 12, the pressure required for a flow of 4.2, and the number of gallons per minute you would get with a pressure of 5 psi. So when we're looking at this, we need to determine what kind of relationship is here. Is this a direct relationship or is this an inverse relationship? And it kind of, we can look at our x and y's and we can set up different variables, but we can tell because we have the gallons per minute and we want to find the psi. So I'm going to say that my psi is that dependent variable because the psi is dependent upon what gallons per minute we have. So to get the gallons per minute we have, we want to find the psi. So I'm going to say my independent is x, and that is the gallons per minute, and my psi is y. Now, if you're looking in the book gave these different letters, and they called this one P and they called this one G, but it is independent and dependent variables. You can name them however you choose. So let's look at the values that they've given us. We're going to write our x and our y. By experiment, we found that when it was 3 gallons per minute, our pressure was 10. And we found that when it was 6 gallons per minute, our pressure is 40. And we can find that this is times 2, and this one is times 4, but we can see through our multiply, we know this is 2 squared. So we know if we multiply x by 2, we're multiplying y by 2 squared, which makes me believe that my function is going to end up being y equals some constant k times x squared, and I notice that from here. So now if I want to predict 12, look, that is times 2, so we can do this one just by keeping the pattern that they have. Predicting 12, this one I'm going to want to multiply it by 4, which is 2 squared. I'm going to get 160 psi. And that works for when we continue the pattern, but where does that work for something like 4.2 gallons per minute? If I want 4.2 gallons per minute, I'm going to have to find my particular equation from my general equation. And the way to do that is to plug in the data points that we have. We're going to just use our first data point right here, this 3 and 10. This one right here. and we're going to just plug it in. So we see that y equals 10, and we have some constant k. That's what we're trying to find so that we can get a model. And then we have 3 for x, and it's squared. And I can find, if I get k by itself, 3 squared, that equals k. I can see that 10 over 9 equals k, which means my particular equation, my equation for this problem, is y equals 10 over 9 times x squared. And now I have a model for this type of problem. I can use this to predict that what kind of pressure I'm going to need to get 4.2 gallons per minute out of that hose. And I will put that in like y equals 10 over 9 times 4.2 squared. Easy to solve with our calculators. Right? So then we'll put it in our calculator and we'll find that this equals, and you should try it so that you know your calculator's working, 19.6 psi is needed to get 2.4 gallons out of the end of the hose. And lastly, we see here the number, what if we want to work this in reverse? The number of gallons per minute you would get with the pressure of 5 psi. So if we know the psi, we know our psi is y. So we're going to plug that in there. So we'll say that y5 equals 10 over 9, because this is our exact equation, x, because we don't know how many gallons per minute we're going to get, squared. And we can find this one exactly the same as we did before. You can do this by multiplying the reciprocal or doing it in 2 steps. We need to get x by itself. So to get x by itself, we will multiply by 9 and then divide by 10. Do you see that? So I will multiply by 9 and then divide by 10. This side cancels out, and we will have 9 over 10 times 5. And that is going to give me, using your calculator, you'll get 4.5 equals that x squared. And we know that we're going to square root it, and that will give me approximately 2.12 gallons per minute. And you'll see that it's rounded because taking the square root in your calculator gives you a long decimal, a nice irrational number that does not repeat. So that is how we would use these with our whole numbers. This is chapter 7, verse 11, using whole exponential values for that n. And in chapter 8, we were going to, before we move on to chapter 8, in the rest of chapter 7, they apply those properties to linear with adding. And you can see, you can try a few where you would, if you add to x, you add to y. It's a adding constants adds to both sides. You'll see the equation, the graph would just adjust, as we've seen with other things that we have graphed. And we have add multiply property of exponential functions. So if you add to x and it's exponential, you're multiplying y by that constant. So you keep multiplying it more. And then, as we have already seen, the multiply property that we used in our example. But now let's move to section 8.5. 8.5 tells us that real world problems rarely have whole numbers, and we end up using fractional numbers. It's not whole numbers. So what does that look like when we're doing this, when it's a non-integer exponent? That's the word I was looking for. So I'm not going to review like our equation. We know our equation is going to be that general equation, which is y equals k times x to the n. And so here's the example that's in your book. As an example, the area of an egg's shell is directly proportional to 2/3 the power of the mass of the egg. So let's look at this one. It's directly proportional, which makes me think it is multiply, not divided. And it's proportional to 2/3 the power. So that's making me think that my n now would equal 2/3. So we will have our equation. We'll let S equal the number of square centimeters and M equals the number of grams of the egg. So they say, suppose a normal 60-gram chicken egg has a shell area of 28 square centimeters. So we're going to use our general equation and we're going to try to find that K right here. So we set S, the number of square centimeters, which is also Y. It is the dependent. And this one is, the grams is independent. So that one would be like our X. If we were to graph this one, you would find it there. So to find our particular equation, we're going to use our values that they have given us, the 60 grams and the 28 square centimeters, and we're going to plug it in to find that K value. So S would equal 60. We're going to find our K. Oh, no, I did that backwards. Sorry, guys. S is the shell. It's the 28. 28 square centimeters equals our constant K times the mass to 2/3. Now, we're going to just use our calculators, and then we'll take 28 and we'll divide it by 60 to the 2/3. We do not have to manually do this, and we'll find our K. Plugging it in has me find that my K is approximately, now I will store this value in my calculator and use its exact value each time. But right now, I'm going to just give you an approximation, which is 1.8269. So that is our constant that we will be using in our particular equation, which turns it into Y, or actually in this case, they want it to be S. S equals 1.8269 times the mass to the 2/3, because very rarely do we have whole numbers. And in this equation, they said, the book asks us to do a couple of other things, and they say, use this model, which now we have our model. This is our mathematical model right here. They want us to use our model and find what happens if the mass of an egg is 1,600 grams. And how would that work? Well, that would work by putting in that 1,600, raising it to the 2/3, and multiplying it. Oh, they rounded it quicker, so they rounded here this to the 7. So 1.827. But we still use the whole value in our calculator. So this is where they would plug it in, use their calculator, find out that S is 249.92. This is the square centimeters. And we're going to approximate this one because it's pretty close to round to 250. So the ostrich egg has about 250 square centimeters of shell. And we can also use this in reverse. This would be, I think I used for the second class, but not the first. The book asks us to find if we have a lizard egg that has a mass of 0.6, I think. Let me double check that. Yeah, they said 0.6 square centimeters. Oh no, we know the shell. 0.6 square centimeters of shell area. And the book says, if we know this, can we find the grams? Can we find the weight? The mass, not the weight. Can we find the mass? And we can, because we will put in 0.6 for S, and we'll use our model, 1.827, and we leave M, because we're searching for M, to the 2/3. First thing we're going to do is we're going to divide to get M by itself, 1.827, 1.827, and then we would find, I'm not going to simplify to the end, I'll use my calculator once. We're going to say that that equals mass to the 2/3. Now, using our power rules, you know, if we raise this one to a power, it's multiplying, so we'd raise both sides to a power. we want to raise this to the 3/2. Because when we raise 2/3 to 3/2 and we multiply them together, we get just straight m. But if I do it to one side, I do it to the other. 0.6 over 1.827 raised to the 3/2, all calculator work. And that will give me the answer of the mass equals 0.19 grams. So that was a recap of what we did in class. Please look at your sections 7-11 and 8-5 to look at a few problems in here and maybe look more at the examples. And I will see you in the next video where I will talk about section 8.6. Thanks.